Quantum postulates are the ground rules that qubits follow. They basically tell us how we can represent them, transform them, and measure them. So basically, there are 6 of these postulates, and we'll be looking at them one by one. Postulate 1 tells us how we can represent a qubit as a superposition of ket0 and ket1, where these two numbers are the coefficients of ket0 and ket1 and are also known as amplitudes. So we know ket0 is a column matrix with 1 and 0 in its entries, and ket1 is 0 and 1. So when we multiply these coefficients with them and sum them together, we get a column matrix like this, wherein these are amplitudes, which can be complex numbers. And when we take their magnitudes and square them together and then add the two, we get a sum of 1. And why is this will be explained in a postulate that is coming next. And this qubit can be represented on a block sphere by the help of these amplitudes. So basically, a postulate 1 tells us that we can represent our qubits as a superposition of ket0 and ket1 in the form of a state vector, or you can call column matrix, or basically a ket. Postulate 2 tells us that we can transform any given qubit state into any other state by applying a particular operator on them. In this animation, the operator applied is Z operator, which means that there will be a 180-degree rotation about the Z axis. This is the Z axis, the vertical axis, and a 180-degree rotation about it gives us from a positive direction of X to a negative direction of X in our qubit state. So this basically tells us that we can apply an operator on our ket state and then get a new state, which is again observable as a physical system, because we know that our qubits are basically physical systems. They can be represented as the quantum spin up or down as explained in Stern-Gerlach experiment, or they can be the electromagnetic proportions of light that there are. They just need to be perpendicular to each other. So basically, postulate 2 tells us that if we have a qubit, we can transform it into any other state and then observe it. Postulate 3 tells us that whenever we apply an operator, then when we measure the result will be the eigenvector of that operator. Because we're talking about Z gate, so we'll look at what its eigenvectors are. So earlier we saw that Z gate or Z operator is basically a 180-degree rotation about Z axis, something like the rotating Earth on the screen. So if you don't know much about eigenvectors, then there is a description, a link in the description, which is really helpful. So you can go through it. Basically, eigenvectors are any vectors upon which, if we apply a given matrix, Z gate over here is a transformation, and mathematically it's represented as a matrix. So when we apply it, that particular vector will not rotate. So if we were in the positive X direction and apply the Z gate, we see a 180-degree rotation. If our initial state was positive Y direction, we still see a 180-degree rotation. But if our initial state is coinciding or is parallel to the Z-axis, then that state is the eigenvector, because it is unaffected by any rotation about the Z-axis. So for this particular operator Z, the eigenvectors are ket0 and ket1, and they are the ones that will that the qubit will collapse into upon measurement. Why are we talking about Z operator specifically? Because in Stern-Gerlach experiment, we established that ket0 and ket1 is the deflection of the electron upwards or downwards respectively. So by default, we consider Z-axis as our default axis, and we consider our measurements about it, because we also represent our qubits in terms of ket0 and ket1. But we can easily transform our qubits into the X and Y basis, but conventionally we take the Z basis to be the default one. So whenever we'll measure a qubit in superposition, it will either collapse in ket 0 or ket 1 because they are the eigenvectors of the Z operator. So now we know that if we'll measure our qubit, it will collapse into ket 0 and ket 1, but we do not know the probability. So for that, we follow this rule. This ket psi is basically a qubit, and it's in the superposition of ket 0 and ket 1 with alpha and beta as the amplitudes, which are basically complex numbers. So we've seen in our previous video on direct notation about how to get inner products. So the rule says, or basically this postulate says, that if we want to find the probability of this qubit collapsing into ket 0 state, then we have to take the inner product of 0 and psi state and take the amplitude of it and square it. So when we do take this and open psi ket and put this equation given over here and then multiply each corresponding term, then we get an equation like this, wherein the inner product of 0 with itself gives us 1, and of 0 and 1's inner product gives us 0. Because 0 and 1 are orthogonal, therefore their inner product will be 0. If you don't know how this happened, you can check the video on direct notation. So we substitute these with the corresponding numbers and we get alpha amplitude square as the probability of being in ket 0 state. Similarly, when we find the probability of being in ket 1 state by the same process, we get amplitude of beta square as the answer. So basically, whatever is the amplitude or coefficient of ket 0 and ket 1, we take it and square it, and that is the probability of being in that state on measurement. So we know that when the qubit is not yet measured, it's in the superposition of these two states, but on measurement, it collapses into one of these. And now we know the probability as well. Earlier, I told you that the sum of these coefficients squares is equal to 1. That was because this maintains the law of probability that sum of all events should equal to 1. And that is because because the inner product of psi with itself, that is the qubit with itself, is 1. And these are the sub-events of the qubit. That is, we know that the qubit exists, right? So the qubit exists and the probability of that is 1, which is denoted by this inner product. And then on measurement, we can get either ket 0 or ket 1. So these are our two sub-events. So we take their probabilities and these are the probabilities alpha square and beta square and sum them up together. So that should also equal to 1. So the simpler version of the rule is that the probability of measuring a given state is amplitude square, and amplitudes are alpha and beta over here. Also, you cannot measure anything but ket 0 and ket 1 in this case because the qubit collapses into the eigenvector of the operator applied, and our default operator is z-axis. So the eigenvectors of z-axis is ket 0 and ket 1. Therefore, we get the probabilities with these two options only. If you want to measure for x-axis or y-axis, you will have to transform the qubit state. More on how qubit states are transformed is in the next video, which is about single qubit gates, which are basically transformations of qubits from one state to another. So the fifth postulate tells us that once you've measured the qubit, it collapses. And again, it collapses into either of the eigenvectors of the given operator, which in this case is z-axis. And therefore, the possible eigenvectors are ket 0 and ket 1. So when the qubit is in ket 0 state, it is in 100% probability of being in ket 0 state. But if it is in the positive bidirection initially, and we measure it, then it has 50-50 chances of being both ket 0 and ket 1. Why? Because this positive direction of y is basically ket 0 plus I into ket 1 divided by under root 2. So the amplitude of ket 0 is 1 by under root 2, and that of ket 1 is I by under root 2. And if we square these amplitudes, we'll get half and half. just like we learned in the previous postulate. Therefore, their probabilities are half and half. And similarly, for the positive direction of x-axis being our initial state, then that is basically ket plus, which is equal to ket 0 plus ket 1 divided by under root 2. So both the amplitudes are under root 2, and if we square them, we get half and half. And that is what this graph shows, that on measuring this, it could either be in ket 0 state or ket 1 state for 50% of the time. And if you sum these two together, then you get 1. So that also satisfies the law of probability that we discussed in the previous postulate. Then the last postulate says that if we have a given state vector, then through a duration of time, we can apply many operations on them. These operations are the ones like the Z operator that we've taken an example for as an example in this video. And one after the other, we can apply different operators, and then we will get a new output state. And how do we calculate it? We take the initial state and keep on multiplying these operations to it based on time, according to which operator was applied to it first. So T1 was applied first, so we multiply it first, then T2, and so on till Tn. And then the result that we get is our new state. So this is very important for understanding single qubit gates, and more on this will be there in the next video. So this postulate basically tells us that if we know the initial state and we know the final state, then we can go in both directions to achieve both the states by applying the correct matrices or operators in this case, which are basically matrices. Why? Because our state vectors are matrices. So for us to transform them, we actually have to multiply them with another matrix. So these transformations are basically nothing but matrix multiplications. So more on this will be in the next video, and these were the 6 postulates. Now we'll be summing them up. What do these postulates really tell us? They tell us how to represent a qubit. That is a superposition, and it is represented as a ket. That was told to us in postulate 1. Then once we have represented the qubit, it tells us how we can transform them using operators. Now we have a given qubit, then we can transform it into any other qubit on the block sphere. Now, if we have done that and we want to measure the operator, then what are the possible results that we'll get are basically the eigenstates of that particular operator. Because we were taking Z operator as an example in the whole video, so the eigenstates are ket 0 and ket 1. So now we know that we can represent a qubit, we can transform it. If we measure it, then it will collapse into 2 given states, ket 0 and ket 1. But then we want to know what is the probability of getting into ket 0 state or ket 1 state. So for that, we get probability by taking the eigenvector for whom we are measuring the probability and the qubit as the psi qubit in the video, and take their inner product, take the amplitude of it and square it, and that is our probability. So in a given qubit, maybe a qubit could be 70% in ket 0 state and 30% in ket 1 state. But after measurement, it will either be ket 0 and ket 1 fully, 100%. So before measurement, our qubit is basically in a probabilistic nature. It is in superposition and it exists in both ket 0 and ket 1 states. But after measurements, it is deterministic. It's a well-defined state, like 0 and 1 as classical bits, and it's not in a superposition anymore. So this also leads us to the point that basically classical states are a special case of quantum states, because quantum states can be in all states, but once measured, they are either 0 or 1 like classical states. And the last postulate tells us about time evolution, that if we know our output state and we know the initial state, then we just have to reverse the order in which we apply the operators, and we will get both the states. So basically applying these operators on our qubit and getting the final state is a reversible process. From the final state, we can get our initial state back. So these were the 6 postulates of quantum computing, and they are very important because they tell us how to represent qubits, transform them, what will we get on measuring the qubits, what will they collapse into after measurement, and what is the probability of being in either of the two states. And how do qubits evolve with time with the application of a lot of transformations on them. About the last point, more on it in the next video. Thank you for watching this one.